All right. So the first step is you are going to design an analog filter with the digital specifications are given. You convert it to analog specifications and then you design the filter. Second step is you design the analog filter. Already digital specifications you converted to analog. And in the analog, remember what you're going to do? You're going to design the analog filter. In the analog filter, you must always go to this step. Which step? This one. No matter what you're going to design the low pass filter, then you transform to whichever low pass or band stop. Remember that. So when I say design of the analog filter, it refers to designing the respective low pass, high pass, band pass, or whatever it is, depending upon the question. Next step that you will follow is what? Now you are in the analog domain. You are asked to design the digital filter and you have mapped the digital specifications, right? You have converted digital specifications to analog specifications. And you did the analog design in the second step. That too, you will design for the low pass filter and you will transform it. Now, once the filter is designed, at this step, what is there? Analog filter is designed. Now, what you should do, obviously, the last step would be what? You will transform. When I say the analog filter is designed, you will have your h of z. That is the meaning. Okay, this is the inference. If I say the analog filter is designed, you will have your response. H of j omega you will have, not h of z actually. You want h of z. So you will have your h of j omega right now, magnitude. So what do you do next? You will transform it into, transform what? The transfer function. The transfer function, that is your h of j omega, whatever you're having, transfer function, that is the design filter of the analog prototype. This filter is called as your analog prototype. Okay, this analog prototype, you will convert it into what? Its equivalent, digital transfer function. So digital transfer function means I will convert it to h of z. So you see here, the important thing that you need to remember is this omega term. Omega term, you have transformed it into its z term. That is the actual meaning of this transformation. Okay. So if a digital specification is given, you convert it to analog specification, you design the analog filter, and even if an analog high pass filter is asked to design, you will design the normalized low pass filter first and then do a transformation to the respective filter, high pass filter say. After that, you will transform the designed analog filter to the digital filter. So this is the procedure we are going to follow from now on. Any doubts here in the steps? Design of the digital filter is very important. These are steps we are going to follow for the further throughout the chapter. Any doubts there? No? Nobody is answering me. Don't sleep. Tell me if you have any doubts. Anybody has got any doubt, because this is very important. You don't understand here?
No, ma'am.
Okay, okay, fine. So I assume that everybody has understood. Without getting this or without understanding this part, it's very difficult to understand further. So make it very clear, note it down, put star mark and keep it, because this is what forms our next type of, for the next few classes, this is what we'll be discussing with. So next thing, important thing, in your IIR filter, right? Why is it coming this? Okay. Your IIR filter, basically, there are two kind of filters we are going to study. One filter is called as Butterworth filter. Okay. One more is your Chebyshev filter. Chebyshev, there is type 1 and type 2. So these are the types of IIR filter we are going to study. So first let us take up our design of Butterworth filters. Okay. So the important characteristics of this Butterworth filter is that in your pass band, okay, you have a smooth pass band, okay, and in case of Chebyshev filter, the pass band is having ripples. Pass band, this is the pass band, right? If you consider a low pass filter, this is your H of j omega, this is your omega. So, say if you consider this is your Butterworth filter, it look like this. Suppose you are considering a Chebyshev filter will have ripples, too many ripples in the pass band. The number of ripples also you have a formula to find out. We'll see that later. Okay, this is your H of j omega, right? So in your Butterworth filter, the most important characteristic is that the pass band of the filter will have smooth transitions. There will be no ripples. Of course, there will be some small amount of ripple present, delta P. Okay, so this is the important feature. So in your Butterworth filter, if you want to find out the magnitude response, it will have a function like this. So please note it down. This is the standard frequency response equation, which is given by 1 divided by 1 plus omega by omega c, where omega c is nothing but your cutoff frequency, and the capital N is given as the order of the filter. This whole thing to the power 1 by 2. Okay, write down this, everyone. Here, what do you mean by N? N is nothing but the order of the filter. Okay, N is the order of the filter, and your omega c is the cutoff frequency. What do you mean by this? Actually, in your even in your LIC or in your AAC and all, you would have studied, right? What do you mean by cutoff frequency? That means, suppose I have a unit magnitude filter. Suppose I have a filter with unit magnitude. Magnitude is 1. Okay. This is the low pass filter I have. Say this is what is given. Okay. So I will take 1 by root 2 of 1. 1 by root 2 of 1 is nothing but 1. Right. 1 by root 2 of this value. Whatever is the maximum value I take, that is nothing but 1 by root 2. So at this 1 by root 2 point, I'll drop down a perpendicular line on the x-axis. So this is called your cutoff frequency. This is how you actually define it. Okay, magnitude is 1 by root 2. For a unit filter of unit magnitude, the cutoff frequency is defined as the value at which the magnitude value is equal to 1 by root 2. Okay, so suppose your filter is like this, and say an order of the filter means what? I'll tell you in short. Suppose you consider a simple low pass filter is like this using analog components R and C, right? This is a first order filter. That means only one RC section is there. Suppose I have one more section for the same cutoff frequency, say 50 hertz. I want to design a filter. What is the equation? I'm little bit going back to your AEC. F is equal to 1 by 2 pi RC. You will substitute say R is equal to 1 kilo ohm. You'll find out the value of C. You will design the filter. This is the filter you have. Suppose the order of the filter you keep on increasing. Now the order of the filter is 2, second order filter, right? Suppose you add one more RC section, okay? You add one more RC section. What happens? What
Ma'am,
happens?
as we go on increasing the reactive components, it will match to the ideal characteristics of the filter, ma'am.
Okay.
That is the
So
slope is there that would reduce, ma'am.
correct. So as you increase the order of the filter, what is going to happen is you will reach near ideal characteristics. That means I'll show you practically how it looks. Okay. Suppose I want a low pass filter. I have a low pass filter, H of j omega. Okay. And the ideal response is supposed to be like this. This is the ideal low pass filter. So the cutoff frequency is there. Before cutoff frequency, you pass everything. This is your pass band. This is your stop band. Okay. Now, I'll show you the effect of the increase in order of the filter. So if the order of the filter is increasing, you will approach your ideal characteristics. How is it? So for one value, suppose n is order of the filter is 1. First order filter means you may get something like this. So this you say your order n is equal to 1. Suppose I say some order n is equal to, this is some order of n is equal to 15. Okay. Say order of the n is equal to, suppose n is equal to 20 is there. My filter will be much nearer to, if you see this characteristics, this will match that of your ideal characteristics, which will be similar to your ideal characteristics. So that is what you mean by increasing the order of the filter. So as order of the filter increases, your filter approaches near ideal characteristics. So whether it is low pass filter or high pass filter, whatever it is. So for our reference, we will continuously take low pass filter and we will explain. Okay, getting me? Just give me one moment. Yeah, okay. So I hope you have understood this. Okay, and there are few observations which you need to understand with respect to your Butterworth filter. Okay, what are those? I'll write it down. You please note down first, then we will see in detail. Firstly, your h of j0, that means your magnitude value for, if it is 0, omega value is 0 means what? It is 1, right? For a unit magnitude filter for all n. Okay, these are few observations from the previous diagram you should write down. So mod of h of j omega, when it is equal to 1 by root 2, what is the meaning? Your omega is equal to omega c, right? You see here, you observe this diagram. Magnitude, unit magnitude filter you are taking. Unit magnitude filter. Considering, write this diagram and then you write down whatever I am writing. So this is 0. So h of j 0 means when omega is equal to 0, what is the value of this h of j omega? It is 1, right? That is the meaning. When omega is equal to, or your magnitude is 1 by root 2, when omega is equal to omega c. So if you take the log value, you know it is 3 dB frequency. Whenever we say cutoff frequency, we also call it as 3 dB frequency. Why is this? You can try in your calculator. If you take 20 log to the base 10 of h of j omega. This is the value you will get in dB. Okay. If you substitute here you put here 1 by root 2. Okay. The answer you get will be 3.03 something dB. You can try and see. Minus 3.01 dB. So what it means is, when you come, if it's in dB, you have this in dB scale. This is the 0 if you consider. If you come below, it is minus 3 dB, right? Minus 3 dB, whatever you are taking, this is nothing but your cutoff frequency itself. Okay? Minus 3 dB if you come down in your log scale, it is equivalent to getting your cutoff frequency value on the x-axis. That is the meaning. Okay? Next is, suppose your h of j omega tends to 0, that is the magnitude itself is reducing to 0, what will be the value of frequency? Obviously it is infinite, isn't it? If you cut off, your omega value goes to infinity, it will be like a straight line here on the x-axis. That is the meaning, right? So omega value you don't know, infinitely long it can go. Got it? That is the meaning of this. So these are few properties, whatever I'm writing now, few properties of the Butterworth filter by observing the unit magnitude response. Then one more characteristic is that if you want a maximally flat filter, you have heard of these things in your maths, maxima and minima, right? So if you want to find the maxima point or the maximally flat filter means, this is nothing but your ideal filter. Something like your ideal filter you want, you can introduce your differentiation concept here. With respect to omega, you do the differentiation, nth order this thing, and evaluate it at omega equal to 0. For n is equal to 1, 2, until the order of filter is 2 times n minus 1. This is the standard representation to find the maxima point. Okay. Last point is that h of j omega is a monotonically decreasing function. All right. So these are the characteristics of your filter, and of course there are a few more things that we have to see. The ideal characteristics I have already told you what it is. Okay.
Ma'am, fourth equation once you explain that point, I didn't get me.
Maximally flat response. See, ideal filter characteristics means if it's a low pass filter, you should have pass band like this, you should have stop band like this. Omega, this is h of j omega, right? So if you want to find the maximally flat response, actually fourth and fifth point is there together. So if you want to find the maximally flat response, or you do not want any ripples in the pass band, you want to get an ideal filter like this, then you can try to evaluate the maximum point or the actual value of your cutoff frequency, actual value of omega, for which you will get ideal characteristics, or the actual value of the order of the filter for which you will get near ideal characteristics, or the maxima point. Usually to find maxima minima, what do? You differentiate it, the function, and equate it to 0, right? A similar concept is told here. Okay. Have you got what I'm telling?
Yes, ma'am.
Okay. So just go through these points. Okay. There's somebody who someone has come. I'll just go and come back in 2 minutes. You can take a break of 2 minutes. I'll come back just a minute. if you equate the denominator to 0 and find the roots of the denominator, what you're going to get? You'll get the poles of the equation. So considering this, what we are going to do is, we'll take our Butterworth filter's response, h of j omega. What is h of j omega? Magnitude of h of j omega is given by 1 divided by 1 plus omega by omega c whole thing to the power 2n, denominator to the power 1 by 2. So this is the magnitude response, magnitude frequency response that is given for a Butterworth filter. Magnitude frequency response. Why is it just magnitude? Because we're taking the mod of that. Okay, we are not concerned about the phase of the signal. Now what we'll do is, I will tell you in general, when you design an analog Butterworth filter, I told you, whenever I say it is analog domain, it is the S domain or the Laplace domain. You have heard of this Laplace term. And when it is digital, okay, remember, you will get the Z. So when I say the analog domain, you will write it as the transfer function as h of S, whereas whenever it is digital, you will write it as h of Z. Please remember this. Okay. Now, I want to write the response, squared magnitude response first. Squared magnitude response. How will I write this h of j omega? I will take the square of this. Why am I taking the square of this? That square root 1 by 2 term will get eliminated, and I will be left with 1 plus omega by omega c whole thing to the power 2n. Okay, where n is nothing but order of the filter. Right? So higher the order, remember, the better is the response of the filter, but you should have a minimum value of this order of the filter such that you do not randomly increase the size of the filter. Because if I say 50th order filter using RC components, what will you do? You will have 50 sections like this. Can you imagine that? It will be like too much, right? So the system that you have designed becomes very bulky. Okay, becomes very bulky, which you cannot afford to have. So therefore, you should have a particular value for this order of the filter n. We will also derive an expression for the Butterworth order, how to find the order of the Butterworth filter. So suppose I can split this magnitude term into its equivalent positive term and the negative term. So h of j omega, I'll write a subscript n here, saying that is the nth order response. So hn of minus j omega, I'll write it this way. It is possible for me to write it like this. So this will be equivalent to 1 by 1 plus omega, considering your omega c is equal to 1, because if you remember, I told you, you will, no matter what, okay, no matter what you have to do, you are going to first design a normalized low pass filter of cutoff frequency equal to 1. So if I put omega c is equal to 1, I am left with this omega whole thing to the power 2n. Right? Okay. So now I want to replace this, since I'm going to do the analog design. Okay. Since I'm going to do the analog design, remember, it is this S that I'm going to substitute. So in most of the cases, you will replace S with j omega, right? So I am going to replace j omega with S now. So why I am doing all these things, I will tell you. You're going to find the transfer function for your h of s or your h of z, whatever you have, the denominator term, right? Denominator polynomial, you're going to obtain the ready-made form. Like for FIR filters, I told you the general expression for low pass, high pass, everything, right? Similarly, every time when you solve a problem, something has to be there ready-made to you, right? So that ready-made thing we are going to derive now. You will understand. Just concentrate and try to understand whatever I'm telling. First thing, remember, you are going to design the analog specifications first, and then you will convert it to digital. So if you have to do that, first thing you are going to do is design analog filter first. And which analog filter are you going to design? You're going to design a normalized low pass filter, and then you'll do whatever it is. No matter what, just remember this. First thing you're going to do is you're going to design an analog low pass filter with cutoff frequency 1. That's it. So even to do that, the denominator term, you have to obtain the denominator polynomial. To obtain the denominator terms, we are trying to do we are trying to solve the denominator term in a general way. Got it? That is what we are doing now. Okay. So if you have this h of j omega, I want the analog specification. So if I want analog specification, I'll write my j omega value as hn of s into hn of minus s. Okay, is equal to, if I replace s with j omega, I should replace omega with what? S by j, right? So this becomes 1 plus s by j whole thing to the power 2n. Okay. So now there are no, one important thing that you need to write is, there are no finite zeros here, because numerator term is 1. Okay, numerator term is 1. There are no zeros, but poles are present because denominator term is there. So to find out the poles, okay, what you should do, take the product, that is equate your denominator term to 0 and find out the roots of that equation. You equate it to 0 to find the poles. If you wanted to find zeros, numerator terms, if there are variables, you will equate it to 0. But since there are no variable terms, you do this, equate it to 0, and now you solve it. So at the end of this, right, we will get the polynomial equation for the denominator. Remember that, which you will use in all the problems. So now, what is the value of s? S by j whole thing to the power 2n equal to, you send this to minus 1 this side. Okay, you want s term, so what you will do is s is equal to minus 1, raise LHS and RHS, multiply j here first, send the j power 2n term, s power 2n is there, like this. So if you want s, you will raise both the power to 1 by 2n minus 1 to the power 1 by 2n into j. This is what you will get, right? Now, from your DSP concept, from the DSP, okay, we know that your minus 1, okay, minus 1, you can write it as multiples of e power j pi, odd multiples of j pi. If you write it, it is minus 1, right? Okay, where k is equal to, 1 minute, yes. Okay, sorry students. Yeah, so what I was saying is, yeah, minus 1 and e power, you can replace this minus 1 with exponential power. Similarly, you can replace your j. J term, you remember? You can replace it with e power j pi by 2. So I'll do this. If I write like this, what happens is your another term comes up, that is your k value, k equal to 0, 1. This will go until 2n minus 1. Okay, twice the number of values. I'll tell you why it is. So you can write this as sk is equal to e power minus 1, you're writing as e power j pi into 2k plus 1. Okay, minus 1 you wrote it like this. This whole thing to the power 1 by 2n. Okay, into e power j pi by 2. So this is it. Now what you're going to do is you will add all these powers and you will be left with, you see, you're going to add the powers and you will write it as a single exponential term. You are only interested in, this is of the form, sorry, this is of the form e power j theta, theta k say. So what is the theta k value? You add all the exponential powers. So you will be left with e power j pi 2k into 1 by 2n. So e power j pi k divided by n. Okay, I'll just write the theta values. Please concentrate and see. You're adding the powers. So you will be left with pi by n into k. Sorry, what did I do? Add the powers, you will get this pi by n into k plus pi by 2n plus pi by 2. Right? This pi by 2 plus this pi k by n, this value. I hope you got it. Right? All of you got? This is what I'm writing it. E power j you have, right? J pi into 2k by 2n plus pi by 2n. Then the outside one more exponential is there. It will be plus pi by 2. So this theta terms together I'm writing, that's all. Okay. Okay. So this is your exponential expression, theta. Now what to do? Why have I written this? And here k varies from 0, 1, 2 until 2n minus 1. So this is the expression that you need to remember for your theta, and you're going to find out the poles of the equation. So you should remember, I have equated this to 0 to find the poles. That means the denominator roots of h of s. Okay, this is what I'm actually trying to find out here. Getting, because the numerator term is 1, there are no zeros in the equation. All you have is poles. How will you find the poles? You equate the denominator terms to 0 and you find out the roots. At what all points you will find out the roots, right? At what all points you will find roots. That is given by this theta expression for k equal to this much. So you substitute the value of based on the order of the filter. Suppose the order of the filter is given as for different values, we will just see it. Okay. Suppose the order of the filter n value is 2. What happens? K will vary from 0, 1 until how much? Until 2 into 2, 4 minus 1, that is 3. 0, 1, 2, 3. So in the denominator, you will have totally how many roots? You will have 3 roots. That means you will find out theta 1, theta 2, theta 3, theta 4. Substitute values and tell me here in this expression. For substitute n is equal to 2, and substitute k equal to 0, 1, 2 and 3. You can also, instead of theta 1, 2, 3, to avoid confusion, you can write it as, okay, theta naught, theta 1, theta 2 and theta 3. Okay, let me rewrite it, no problem.
Ma'am, for theta naught, k value will be 0 in that way, ma'am.
Yes, yes, yes.
Okay, ma'am.
Okay, meeting will end in 5 minutes. You rejoin everybody after that. Theta naught, k equal to 0. What is the value you will get? You will get theta 1, theta 2, theta 3. So theta naught means what? It is pi by 2 into 0 plus pi by 4. N is equal to 2, right?
135 degree.
Plus pi by 2.
135 degree, ma'am.
You keep it in pi value only. Pi by 4 plus pi by 2 is 3 pi by 4. Right? Theta, put k equal to 1. What is the value you will get? Theta 1 you should get 5 pi by 4. Theta 2 you will get, all of you do it, 7 pi by 4. Actually, it will be odd multiples, that's all. 9 pi by 4. So for a given value, okay, for a given value of n and values of k equal to 0, 1, 2, 3, given value of n, the value of k will vary from 0 to 2n minus 1. So depending upon the value of n, those many roots will be there in the denominator. So roots in the denominator are nothing but poles. So if you have h of s as some value, most importantly it will be of this form, 1 divided by product of s minus sk. It will be like this. Okay, are you getting what I'm telling? It will be of this form. Your answer, all of you can have a look at this. This is how your h of s is going to look. Because numerator for your Butterworth filter, the main characteristic is you will have a smooth pass band, so you will not have numerator term, zeros will be not there, only the poles of the system is present. Okay, so for each value of n, even for n is equal to, for one more value you can do and write and keep, for n is equal to 3, what is going to happen? K will vary from 0, 1, 2 until 2n minus 1 means how much? 2 into 3, 6, 6 minus 1, 5. So 0, 1, 2, 3, 4, 5. You will have 5 roots. 2n minus 1 means 5. 5 roots in denominator. That means there are 5 poles for this question. So what are the values of theta naught, theta 1? You can find out and write and keep. Why I am asking you to write and keep, you will understand. Theta naught, theta 1, theta 2, theta 3, theta 4, theta 5. So values are 2 pi by 3. You can substitute there and you can write and keep. 2 pi by 3, pi, 4 pi by 3, 5 pi by 3, 2 pi, and theta 5 is 7 pi by 3. I hope all of you are getting this. So physically, if I have to plot the poles, okay, so I will write it like this. The poles of the equation S naught, S1. So if I have theta naught, it means what? See here, all of you have a look here. If I have theta k value, it means that I am able to find sk, the denominator roots, right? So all those sk values I'm going to plot here. You can plot on a unit circle. Okay? So you can start somewhere if it is S0, S1, S2, S3, S4 in your control systems you are studying, right? Okay. Actually, it comes anti-clockwise.